afternoon, everyone. We've had a very busy few weeks, and so hopefully this lecture is going to be a little down-tempo. We are going to learn one new concept, which I'll introduce to you shortly, but for now, sit back and take a hard-earned relax in your seats after a very busy 3 weeks. You'll notice that today I'm not wearing my usual bow tie. Instead, I am wearing a banana suit, a banana badge, a banana shirt. I even have banana socks. It is a Jewish holiday today, the holiday of Purim. Before we continue with our exciting new content, I want to first approach some of the things we've already learned and see what the implications are for numerical algorithms. These are algorithms that are used in the sciences and biological, physical sciences, and chemistry to perform all sorts of useful numerical computations. One of the most powerful forms of computations that you can do using the techniques you already have are various forms of approximation. We're going to do a linear approximation based on the Newton-Raphson method. In this case, we'll approximate the cubed root of x. Now, given the techniques you have, you might think, well, wouldn't there be a cubed root function in my language? Well, there might not be. And even if there is, it's worth knowing how to apply these techniques to compute a function that might be in a library, so that if it isn't in a library in future, you have the ability to do it. Plus, this begs the question, so how does the library do it? This is what we're going to see. Let's take it as a given for the time being that if you have q equals the cube root of x, then q prime is a better approximation, where q prime is given by this formula here. This is a simple application of differential calculus, where we take the derivative and use that to perform an approximation. Notice that the prime here, though, is not itself the derivative. That's just a note indicating a new variable. So if we've q, then 2q plus x on q squared on 3 is a better approximation than q was itself. X is the number we're trying to calculate the cube root of, and q is our prior approximation. So your first question might be, well, what if we don't have an approximation? If you don't have an approximation already, you can just guess. You can guess randomly. You can guess that the cube root of x is at least a third of x. There are lots of different clever ways that you could guess. The main thing is that you have to have a first step that you're going to put into this program. We can perform this process iteratively. So once we have a first guess, we can make that guess better by getting q prime. And once we have q prime, we can make another guess based on q prime, which is q double prime. And once we have q double prime, q triple prime, et cetera, until some point. Now, when I say some point, what might be a clever way of figuring out when to stop? When have we approximated enough? And
when our approximations are very similar or become very close to each other.
yeah, so this is a great answer. Thank you. When our approximations start to converge, that is when two subsequent approximations are very, very close to each other, we know that our approximations are not improving very much. So what we do in our C code is we're going to detect this. We're going to run our approximation process over and over until the point at which we are satisfied for our use case, and this is going to depend on what your use case is, that we have achieved close enough convergence for this to be an appropriate approximation. Of course, we are operating in C's finite world of limited precision. So when we have our floating point approximation or our double approximation, we know that we're not even going to be able to keep getting better and better, even if the method works anyway, because we're going to be limited by, anyone? Bit louder. Not memory, but in this case, we're going to be limited by the specificity by the accuracy that we can achieve using these floating point numbers. Remember, we saw that floats can get inaccurate if you go to too many decimal places. They can't keep going on infinitely. And so our approximations can't keep getting better infinitely. Maybe we just don't have enough decimal points to represent the number fully, and so our convergence is going to be just good enough. So as we've done previously, we've included our math library because it's going to contain some useful functions that we'll want to invoke in our approximation. So let's go to the main code. Got our usual get in input from the user, and then we request an initial value that we're going to calculate the cube root from. Okay, so this is stored in val, and we run cube root on val and print it to some decimal points, and then we're done. Here is the iterative process that we were talking about just a moment ago. 2 times our approximation plus the number x, or in this case we've called the variable v, on the approximation squared, and all of that divided by 3. And do this to a maximum number of cube iterations. If we go up to the top of our file over here, we'll see that we've set a maximum number of iterations. So even if we don't start to converge, we might still want to set some limit on the number of times we do this process, so as to prevent our program from going way too long, just in case the approximation doesn't converge very well, which might in fact happen. Perhaps it takes thousands or hundreds of thousands of iterations or millions of iterations to get any better, or it's just not working. In that case, we want to make sure that we're capping it in some way. You'll notice we have here a slightly different comparison statement. Our comparison statement here is checking the absolute value of the input. That's what the function fabs is. It's the floating point absolute value. Let me just double check that, because I've forgotten all of a sudden. But we know how to check things like that very quickly. Man, fabs. Yep, floating point absolute value function. So our guess was confirmed. We go back to our code and we see what it's doing. So it sets some lower bound on the absolute value and some upper bound on the absolute value. Let's see what we've done here. 1 times 10 to the negative 6 and 1 times 10 to the positive 6 are our upper and lower values. Why might we also bound fabs behind these? We've just been talking about the limited precision of floating point numbers. What might this be? You're going to have to say that into the mic for everyone.
Isn't that because when there are more and more decimal points, it gets more and more precise. So you have to limit the amount of decimal points to make sure the approximation is as precise as possible.
Exactly. So we know that our floating point calculations become more and more imprecise as we go into further and further decimal places. So we've got to make sure that our number is not actually reaching that limit, which is why we bound it on both sides, both the lower side and the upper side. And then we return. And that gives us the next approximation of our number. Let's give this a run. Clang. Did I delete the for loop accidentally? Oh, there we are. Thank you to whoever noticed that. Sorry, thank you very much. So compile it with the flags, and this was, what do I want to try to get the cube root of? Any number. It's not that hard a question. 27, okay. It works. Now let's try it with a number that does not have a perfect cube root. Pi. Does anyone know more digits? Let's call that pi. Seems to be working. Okay, so there is our example of numerical approximation. Remember the key things to worry about here are convergence of your answer, the maximum number, to set a cap on the number of iterations that it runs for, just in case you're not achieving that, and also to bound it for inaccuracy of floating point or even double numbers. So there is the 3 key things to worry about with numerical approximation. Limit on number of iterations, floating point inaccuracy, and convergence. What I'm going to do is I'm going to leave the program up on screen for a minute, and I want you to turn to someone next to you and discuss what you think it does. You'll have about 2 minutes for this. In Zoom, in the chat, everyone, if you already know the answer in Zoom, don't spit it out for everyone. If you're just guessing, feel free to guess in the Zoom chat. So what does this program do? And I think that's everything you need to see. And I will give you 2 minutes to discuss with the person next to you. Okay, hands up if you think you have an answer. Okay, we're going to take the microphone all the way to the back. Okay, what does EU do?
Checks if a number is odd or even.
Do you want to explain how you came to that conclusion? There, grab the microphone.
Because it just goes back and forth.
And what do we know about even and odd numbers?
They're odd.
Exactly, they're even or odd. So if we go back and forth, if we go back 2 times between, say we start at 3 and we go 3 to 2 to 1, we've gone twice. And so we know that we're still on an odd number. Likewise, if we went back and forth twice from an even number, we'd get to another even number. This is called mutual recursion because we don't just have one single function making a recursive call. We have 2 functions which make a call to each other, leading us to mutual recursion rather than just singular recursion. And the name of the file kind of gives it away. Let's try 5. You can see that if we run it on E is going backwards and so many times that we result in a 0, and oo is going back so many times that we get a 1. Oo is a function that tells us if it is odd, which it is indeed, and E tells us if the number was even. So let's go and look at the code one more time and see if we can realize that from the code. So if we're starting with the number 5 and we make a call to E first, E goes to oo, goes to E, goes to oo, goes to E, goes to oo. We've done that 5 times, and so we end up returning 0. Likewise, if we run oo, oo goes to E, so that would return 1, goes to oo, that would return 0, would return 1, would return 0, would return 1. And because we're bouncing back and forth, and we're bouncing back and forth the number of times of the number that we put in, we end up either getting the 0 or the 1. And you'll notice here we've got our usual structure for a recursive function. We have our base case in both of them, and we have our recursive call. Ooh. And our recursive call reduces the size of the input so that we make progress towards terminating the program. And I presume Zoom has lost screen sharing?
No, we still see it.
The right screen?
Yep.
Yeah, great. Okay, so we can continue on. That's it for our look at recursive functions and functions in general, although we will still be using functions for the rest of the course. Void is a type in C, and it's a type that we use to indicate that the result is actually going to be empty, or that the result has no clear definable type. When we talk about pointers in the first lecture of next week, we're going to be using this keyword quite a lot because pointers allow us to specify places in a computer's memory where we might not know what there is. Likewise, it's okay to declare a function a void function if it doesn't need to return anything. What might be an example of a function that doesn't need to return anything?
This is a guess, but maybe because like the reason we wrote the main function is to sort of utilize it and to extract information from the body.
So when our program ends, does the computer turn off?
No.
Okay, so what might be useful, why might it be useful for the computer to know what the result of main was?
To store that as memory.
Close. What if main returns 0? 0 is normally success or failure.
Fail.
It is normally fail, but let's say for the case of the operating system, it's success. But it's one of those values. Why might we want to know if main has resulted in success or failure? If you're running the computer and you type in your program, would you want to know if the program succeeds or fails? Yeah, so it might make sense. Remind me your name again? Leto. I've asked you a bunch of times. So Leto said that we might not need to return any value from main because main just ends. But Jocelyn reminded us that when main ends, we actually do go back to the remainder of the operating system. And so a success or failure value might actually be useful so that you can know that when you go back into the operating system and are trying to figure out what to do next with the program. But there is an argument on both sides. So it's perfectly acceptable to write your main function with a void, but it also might be good practice to write it with a return type of integer. Same kind of thing from printf. With printf, we're just asking it to do something very specific. We want it to print something to screen. And when that's done, we don't actually need to do anything with the result. However, we might still want to know whether printf has succeeded or failed, so we might make it an int anyway, which is actually the answer. But making a function void is an acceptable thing to do. Just do it judiciously, and particularly in functions that are unlikely to fail in a way that would be catastrophic. So let's check this out in our code again. Here we have two functions that are void. Our main function is still an int, even though it could have been a void and would have compiled successfully. You'll notice that we've used void here as an argument to one of our functions. This is because older versions of the C standard, prior to C23, which I'm very excited about for next year, required you to adhere to the standard if there were no arguments to a function to put in void when you define it. Now, you don't actually need to do that. It doesn't make your functions work better. Your function won't compile any worse because the compilers know that it doesn't matter at this point. However, if you are being very pedantic, like our flag for our compiler, -pedantic, you might want to put that in until we all move to a glorious C of the future. This program, the main point here is just to illustrate the use of void. We are going to scanf in a number, and if the number is less than 0, we are going to print out an error. It's just checking that the user has entered in something valid. In this case, we're just saying for our own purposes that anything less than 0.0 is invalid. We then go into a function called fatal error. Cannot recover, program abort, and then exit failure. And you'll notice here that we're using a special function called exit that exits the program immediately. It doesn't require you to return back to the main function and then the main function to return. It just ends everything immediately. This value, exit failure, is a hash define, but it's not a hash define that you have to make. It's a hash define that comes built into the standard library, and there's also exit success. So let's run this, and we'll run it both with a valid input and with an invalid input. Cannot recover, program abort. Now, in this case, what am I doing with a double that might mean that I want to throw an error if we put in a negative number? Look at the main body of the code. I print the number, and then I'm printing the log of the number. So why might I be throwing an error if the user inputs a negative number? Anyone? Log of -1 is not defined, that's true, but that's only part of the answer. Thank you, Charlie. Emily, are you on chat today? Can't see the list of participants. Haha, don't ask me. That's a fine response. Anyone else? Why might we want throw an error if someone puts in a negative number? If we're calculating a log. Log of -1 is not defined. What else is not defined? Log of less than 0 is undefined. That is correct, Wada. Log of negatives, yes. The next thing to point out is that C is always pass by value. This is in contrast to some other languages that you might have used, including Python, which is sometimes pass by reference. Now, these are both slightly complex terms, so we're going to unpack them. Pass by value means when you give a function an argument, what you're giving the function is not an object. You're not passing the parcel to the other function. The other function is actually making a copy of whatever you've given it. It's more like holding up a sign with the number that you want the function to have, and then the function at the other side scribbles down on a piece of paper and puts up the same number. This is very important because if I over here in the main function say I have a variable x and x equals 3, and now I modify it, I send it to this function, and now I modify it and I make x equals 5. Is this function over here going to see x equals 5 or x equals 3? Put your hands on your head for x equals 5, hands in the air for x equals 3. Pretty much all of you got it. The correct answer is x equals 3. And this is because that function made a copy of what I told it to when I put it up in the air the first time. When I made the function call, I passed it by value. So passing it by value is holding the sign up, and then the other function scribbles it down and holds it back up and uses it in the body of that function. Pass by reference is a little different. Pass by reference is the main function gets a giant number 3 and writes it down on a piece of paper and puts it in front of the ground and says, that's my number 3 over there. Can you use it? And then this function over here looks at that number 3 on the ground and says, oh, yeah, I can deal with that number 3. Therefore, in pass by reference world, if this function over here says, look, there's a number 3, you can use it, and then changes it to a number 5, this function over here will see all the changes get reflected. The key thing to note is that C never does this. C is always pass by value, which means it's holding up the sign and then the other function scribbles it down and makes the copy. This is true even for more complicated objects. Now, some of you might ask, well, what if I actually want this linkage between the two of them? What if I want this function to be able to change the thing on the ground and that function to see it, or this function to be able to change what's on the ground and that one to see it? That is what we're going to look at next week, and we're going to have a clever workaround that plays with the computer's memory in order to allow both of the parties to cleverly agree on what they're exchanging in order to change the actual object. But more on that later. Another way of thinking about this is a photocopier. C functions make photocopies of their inputs and then only modify those photocopies. They don't touch the original. We're finally at the end of the basic introduction to the C programming language. From now on, we are moving on to advanced features of C that are not present in Python whatsoever. These are going to be C arrays, which are similar to some data structures in Python, but also a bit different, and pointers, and then finally some more exciting different things that are like Python objects, which we'll call structs. There are many similarities that we've seen between Python and C, and I'm including these slides because many of you are already comfortable with Python, and I want you to have an easy reference for you to link the two and remember what's the same and what's different. When I'm going into Grok and writing my program, which things do I really need to keep in mind are different. So both are imperative languages. This is mostly true. Both of them don't use this fancy declarative thing where you just tell the computer what you want to happen and it figures out how to make it happen. In both of them, we have to have a very clearly specified set of instructions. There are similar mathematical operations available. There are a lot of shared types of functions. So C has a function to calculate the sign of a number. Python has a function to calculate the sign of the number. There are lots of similarities in the library functions available, although Python's are much, much more extensive. There are also similar control structures. We have for loops, we have while loops, we have if, we have else. So that's not new. And there are also lots of libraries and code out there that's been written for both of these languages that you can use or reuse, that you can borrow, that you can extend, and that you can make your own and incorporate into your programs. There are also a lot of differences with Python. Python is a language that is white space sensitive, so you have to be very careful. Have I got the right number of tabs? Have I got the right number of spaces? Or am I in space land? Am I in tab land? Where's my indentation? Et cetera, et cetera. C is white space independent. If you remember the Star Wars obfuscated code demo that we saw in one of the lectures, you can write C with 0 spaces. You can write your entire program on one line and it will still function. C arithmetic is heavily bounded, so we have the limitations of the finite representation of numbers inside the computer. Python doesn't really have this limitation, at least not in a sense that you would encounter in everyday programming. Python uses bool for logic to represent true and false, so you have true, the value true and the value false in Python. In C, we just use 0 and 1. And then Python is dynamically typed. This is one of the big points that you might not have appreciated so far, but that's actually already making a really big difference to the way you're coding. In Python, if I have a variable x and I assign a string to it, let's say x equals hello world in quotations, and then later on I want to reuse that variable x, but I now want it to contain a number, I can just say x equals 4, and Python will be totally okay with it. Python is dynamically typed. That means a variable can change the type of what it contains, and the Python language will just figure that out. C is statically typed, which means that once you've set the type of a variable, it can't change. Now, you can be clever and do all kinds of things with the underlying memory that the variable is using, but at the end of the day, C is always going to treat its type as the one you assigned it. There are also a few more large and significant differences which might be frustrating. Python includes a bunch of data structures that make getting started with some code quite easy. These are set, list, dictionary, all of these types that you've been using pretty heavily in FoC. But C lets you mess with memory, lets you mess with pointers, lets you throw out everything else other than the core language features, and ultimately gets you much closer to the bare metal of the machine, which means it's much faster, much more optimized, and can do things that Python altogether can't do. Our next segment is the 4 scopes of C. What scope is it defines where a variable is able to be seen within other parts of the program. So remember I had that copying demonstration that I did at the front? If I don't copy a variable over from one function to another, the other function isn't going to be able to see what's stored by the first function. So if I have function A and function B, and inside function A I have variables foo and bar, and I've shown function B what bar is, function B over here will not know what foo is. Foo is closed off to it. It's like there is a black wall and all it can see are the signs held up. This is true in a number of different ways, and in the remaining minutes of this class, we are going to look at the 4 different scopes, the 4 different kinds of barriers that C erects to hide and show variables between parts of the program. The first scope is global scope. If you declare a variable in global scope, that variable can be seen anywhere throughout that program. Function scope is kind of funky. There are 2 of the scopes that we're not really going to use. Function scope is one of them. It applies to labels and not to variables, and these we're not going to look at all in the class, but it's worth knowing that it exists. Then there is code block scope. Remember, a code block is any segment of code that's bounded by our parentheses. So for example, inside an if statement, we have our curly braces, sorry, not parentheses. In a for loop or inside an if statement, we have our curly braces that mark out a block of code. And you can put these anywhere you like in your code. It doesn't have to be attached to an if or a for, but any variables that you declare inside those curly braces are not going to be visible outside those curly braces. There's also function prototype scope, which is, again, outside what we're really going to be looking at, but I put a link there in the slides. And I think I have to upload a new version of these that'll be available for you to click on if you want to learn more about this scope. So to close us off with this segment, we have demos illustrating some of the scope, and any demos that we don't get through will eventually be added in a supplementary module. I know we're a little behind on those. Okay, up at the very top, you'll see I have declared a variable that's outside of any function. This is how we declare global scope. Over here, I have another function, display, which is going to try and print my global variable. And a global variable doesn't have to be called global. It's just an example variable name. And you can see that we will run display inside main, we'll change the global variable, and then run display again. This is like having the variable out in the sky. Every part of the program can look up and see that variable. Let's run it very quickly. Ooh. And I just overwrote that program. Be careful not to do that. It's very easy to do. So now my source file no longer exists. I have compiled the source file into itself. It might undo. There we go. Magic. But you can see it worked. Before the change within main, it was 5, as we declared up the top, and then we changed it after. Okay, now we have a few other demos of scope. This one is illustrating the scope within different functions. So we're going to declare two variables, x and z. I'm going to print them. Then I will run a function with x and a function with z. And this function, func, is going to take in a value and then add 1 to one of them and add 8 to the other one of them. Now I'm going to put this up for a few seconds. We do have enough time, and I want you to figure out what values this program is going to print. So if you have a little pen or paper, write down what you think the output for this program is going to be. Okay, someone in the live audience, given that, oh, there we go. Prakash Kumar says 3, then 5, 4, then 12, 13, then 21. Let's see if he's right. And if I can put 3, then 5, 4, then 12, 3, then 5, 6, then 14, 3, then 5. Every time we run main, you'll notice that we're getting 3 and 5, even though this function here is modifying its input. Why might that be? And we'll take this from the live audience.
It's because when the x and z change within the function, because of the scope, it can't be seen in the main function.
Yeah, and remember that the C programming language is pass by value. Pass by value, exactly. So what's happening is the main function, thank you, the main function is copying the value into the other function, which then runs it. And when that copy is modified inside func, the original one doesn't change. This allows us to reuse variable names inside this function that have nothing to do with these variable names. When func is called over here, it's called with 3 in the first instance. So what happens? The main function holds up a big sign with the number 3, and then func over here scribbles down the number 3. And now, the number 3 is what's stored in this x. This is func saying, okay, I'm going to scroll down number 3, and I'm going to write x underneath it. So,
Is this encouraged, like reuse variable names in different functions?
Is it
Encouraged.
encouraged? It makes a lot of sense sometimes to use very similar variable names within functions that you use within other functions. It's not a bad thing to do at all, but you should just be aware that it might lead to confusion if you do it in an unintelligent way. So it's all about discretion and about the way you structure your program. If I label everything in my program A, B, C, D, E, F, and those are the only variable names I use, that's not very illustrative. It doesn't help you understand the program. However, if you reuse a variable I in lots of places, but every time it's used as a counter variable for a loop, that's totally appropriate. Let's look at our second scope demo. Okay, here we now have Z in global scope and X in local scope. We're going to observe some different behavior this time because unlike the value X over here, the value Z is global. And global values are slightly different in that they're actually stored in a special part of the computer's memory. So they violate the special rule that we have about things being stored within the function's own block. Putting a variable in global storage, now you'll see that every time inside func, X is changing. Outside of func, inside main, X doesn't change. This is because X is a local variable to the main function. But because Z is a global variable, it has this special property that when we use it inside func over here, it's still referring to that one over there. Why is this? This is because the name Z isn't actually declared here. You'll notice there isn't like any int Z and then Z equals something. We're just using it. And in the second time we call Z, this weird and interesting thing happens. So the second time we call Z, its value is already 7. So what happens? We'll do our little hold up sign thing to illustrate it once more. The main function holds up the value 7 to func. Func receives the value of 7 as X, as it sees the value of 7, and it writes down underneath it X. When we get inside of func, X is equal to 7 because we just saw that on the sign. So that becomes 7 equals 7, X equals 7 plus 1. So that's 8. I'm just doing this for illustration. And then that was 8. And Z was 7 from above. But it's not referring to what was passed in and what was scribbled down. It's referring to this global variable over here. So our pass by value rule wasn't actually violated. What happens is that this value was visible because it was written as a global variable. And so it didn't actually need to be passed in. So we could essentially see the value 7 that was updated there, giving us our final value of 16. And let me look quickly to see what the last scope was. And these I think I'll put in a supplementary module. And with that, we close out our introduction to the C programming language, and we're going to move next week to more advanced features. I'm excited to see all of you for another great week. There will be a new recap video, hopefully 1 or 2 supplementary modules when Liam and I finally get around to putting the touches on them. And also start making sure that you're keeping on top of your grok exercises, because assessments are not too far in the future. Thank you. It was great to see all of you, and I look forward to seeing you again next week.